All right, so today we're kind of looking at our last few extensions or tricks here on some of these basic ideas we've been working with. So I just want to reiterate that really the two most common things you'll use when you're looking for angle measures or arc measures in a circle are that inscribed angle, right? This inscribed angle whose point is on the edge of a circle is half the measure of the arc that it intercepts. So this inscribed angle here opens up to the arc of measure 2A. So the inscribed angle must be half of that, right? That's number one trick. Number two is if we have a diameter that cuts a circle into 180 degrees above and below, and if we have a full circle, it's 360 degrees total. So we can always subtract to find the missing portion, things like that. So those two tricks, the whole 180 degrees is half a circle, 360 is total, and an inscribed angle by far will solve like 75 or 90% of the problems you come across, just using those in combinations and over and over. Okay, so that being said, those being your two most common tricks, let's dive into kind of some new consequences that all come from these two right here. There's no new magic. It's just kind of shortcuts that we develop using these two tricks. So one is, let's look at a new version of this inscribed angle. So we know that this point A here opens up to this inscribed angle. So we've got half of the arc it opens up to. So this A to 2A. Well, what if I were to take this point A and kind of just slide it down here? Well, it's still equal to half of that inscribed arc, right? I mean, here's the inscribed angle A. It's half of the arc it opens up to. Nothing's changed. Now, if I slide it so it's really close to C, still, it's just this angle here is an inscribed angle. It's half of this arc it opens up to. But what if now I make it so infinitely close that it actually merges with C and becomes point C? So instead of line AC being a secant line anymore, it becomes a tangent because it only hits the circle at a single point. And look what we have. We have that same angle here, A, still opening up to an arc of 2A. Now we could prove this more rigorously, but I just wanted to show you that. That's my way of viewing this, is it's kind of the extreme situation where we took an inscribed angle, the point that opened up to this, and just slid it down. So it was here. Then slid it down. And the entire time as we're moving it, and slid it a little more. And each time we move it, it keeps that relationship of it's half of the arc it opens up to. And as it gets infinitely close, it's still half of the arc, half of the arc, half of the arc. And nothing changes in that infinitely small blip where it becomes point C. This really is just an inscribed angle of that arc. Now, one little extension of that is, the way I kind of draw it myself, is if we have a circle cut by a tangent, we already knew off to the side, we already knew that this tangent is perpendicular to the diameter. Now that makes even more sense because look, a 90-degree angle times 2 is the inscribed angle of a 180-degree arc. This 90-degree angle opens up to a 180-degree arc. That makes perfect sense now. But in general, what this is saying is now if you have any chord that hits at that point of tangency, it doesn't have to be a diameter, so it's not a right angle. Instead, we get that this angle here opens up to an arc twice as big. And the other side, let's do it in orange here, let's call this angle B, opens up to this other arc, which is 2B, right? And together, this makes, again, perfect sense. Together, these two A and B add up to 180, and we multiply that times 2. These two 2A and 2B add up to 360 because it's a whole circle. So it makes total sense. I put the image in the book in here if you want to write out the more rigorous idea, but I like this drawing up here where A opens up to 2A and B opens up to 2B. Okay, but again, that's really just an inscribed angle. Okay. So now let's look at the idea of where could an angle be, right? An angle could be in the center of a circle, right here. If two lines cross at the center, well, those central angles are just equal to, by the very definition of how we measure arcs, just equal to the arc measure. Because we're saying out of 360 degrees, how many is this chunk, right? How many is this chunk right here out of 360 degrees? Okay, same thing for here. The central angle is just equal to the length of it, or I mean the measure of its arc, right? So if it's 90 degrees here, this is a quarter of the circle here. It's a quarter of a bigger circle. It's a quarter of any big circle, right? Our second rule is, well, what if the angles, or what if the lines crossed on the circle? So what if it was an inscribed angle? Okay, well, we talked about that. That's A to 2A. So we have, what if the angle's at the center, and what if the angle's on the edge? Okay, we dealt with both of those. So center and on the edge, center, it's equal to the arc measure. If it's an inscribed angle, it's equal to half of the measure of the arc. Now the new situations are, what if it's inside the circle but not at the center? It's a totally different spot. What's that relationship there? And separately, what if the two lines were to cross outside the circle, so the angle's outside the circle? Well, using inscribed angles, we could find out the relationship. So let's look at two lines that cross not in the center. So we have some angle here, x, but it is not an inscribed angle. It's not a central angle. It's floating out in the middle of nowhere. Okay, well, let's look at it. So that one first, I'll give you the formula first. You could write it out. So it's just that since these are vertical angles, they're both x, so it doesn't matter which one you choose. But the measure of x is the average of the two arcs. So this arc being A, this arc over here being B. If we add those together, the measure of A plus the measure of B, and then we divide it by 2, we get the average of A and B. That's what x is equal to. Okay, so let's look at why that's true. So that's the equation right there. So the way you could solve it is simply add a single line, and all of a sudden we can just use inscribed angles to solve this, okay? This angle here is an inscribed angle of 50 degrees, so half of 50, this is 25 degrees. This angle here is an inscribed angle of this 150 degree arc over here, so half of 150 is 75. So that's just, you know, your main rule of inscribed angles. Well, of course, this is just a triangle right here. So subtracting from 180, we get those add up to 100. So this must be the leftover 80. And then subtracting from 180, we get this must be 100. So we could solve that if there were numbers, and we just add that single line. So let's do that just with variables now. Let's say we start with an x, and an a, and a b. Okay? Let's add that single line. So this must be 1/2 of A, because it's the inscribed angle of this arc. This must be 1/2 of B, because it opens up to this arc. And then we could use a triangle and say, okay, this is 180 minus 1/2 A minus 1/2 B. That's great. Or, and then we could subtract from 180 to get x. That gets a little algebra heavy. I mean, it's totally fine. 180 minus that. Or another way is using the exterior angle theorem, which is any two angles of a triangle add up to be equal to the exterior angle on the other side. So to save us from that algebra, we could have just said x equals 1/2 A plus 1/2 B. But let's do the algebra really quick, okay? So if we write this out, right, this is what x is equal to. It's 180 degrees minus this. So 180 minus that, let's distribute that negative, and we get 180 minus 180 plus 1/2 A plus 1/2 B. And look, those cancel. And so we just figured out that x is equal to this, which is the same thing as 1/2 A plus B. So again, you don't need this shortcut. I mean, this is a really useful shortcut. If we have any angle not at the center, right? Any angle, this even works. I mean, think about it. This is so cool. If it's an inscribed angle, think about it. X is equal to, well, one arc is this size, and the other arc B is right here, which is 0. And what's the average of A and 0, right? X equals 1/2 of A plus 0. So x equals 1/2 of A. What? Like, it still works even for an inscribed angle. So any angle not at the center, it even works at the center, right? If it's at the center, if this is x and x, this must be x and x. So let's see, one angle, x is equal to 1/2 the two arcs, x plus x, 1/2 of 2x, x, right? So I mean, it works no matter where, but in general, when we use this, is we say when an angle is not at the center of a circle, it is equal to the average of those two arcs, A and B, that it opens up to and that its vertical angle opens up to. Okay? The one other trick we're going to use here is what if the angle's outside a circle? If the angle's outside a circle, then we actually have this 1/2 the difference between A and B. Another way to write this same thing is it's 1/2 big arc minus small arc, because sometimes people write the wrong things in there, and just sometimes I like to just think about it as half big minus small. Okay, so let's look at that. Okay, why is that? Again, if we add a single line, this is really just using inscribed angle. So if I add that single line, this angle here is the inscribed angle of this 150. So it's 75, just half of 150. This angle here is the inscribed angle of this 50 degrees. So this is 25. Finding the remainder of this 180 degree arc, we get that this is 105 right here. And then this is a triangle. So we get x plus 25 plus 105 equals 180. And we can go ahead and solve. We get x plus 130 is 180. And so subtracting, we get x equals 50 degrees. Now over here, let's do that same thing with variables. Okay, I'm going to add a single line here. The inscribed angle of arc B is 1/2 B. The inscribed angle of arc A is 1/2 A. And so again, I'm going to save us some time here this time, and I'm going to say if we add up two angles of a triangle, that's equal to the exterior angle on the other side. So x plus 1/2 A is equal to 1/2 B. Subtracting 1/2 A from both sides, we get our little formula here. So subtracting from 1/2 A, so we get x equals 1/2 B minus A. And this works for any point outside a circle. Okay? So I'm going to add one little extension to this. This is a great formula, and we can use it even as this becomes from a secant line right here. Even as it becomes a tangent line, we can still use it. So let's go down here and look at that. So if it were to open up to a full circle, it's still 1/2 big arc minus small arc. But look at this. If both of these are tangent, we don't need two separate variables. Once we have A, we could rewrite this as the rest of the circle. And this is a common trick that comes up. So for example, if we look at this, we get, okay, x is, and here we put A, then on the other side, we just do 360 minus A because it's the rest of the circle. So here we get 1/2 big minus small, and actually algebraically, if you ever come across this situation, x is equal to the complement, or I mean the supplement of A. And that's something you could add to your sheet of notes if you wanted. Okay, so let's go ahead, oh, there's the bell. Let's go ahead and do some problems, okay? I'll just kind of walk you through these. All right, so here we go. So this first one is actually just an inscribed angle of this arc AB. Again, it's an extreme version of the inscribed angle like this. If we took this point and slid it down and got it closer and closer, closer and closer, and this angle ends up becoming right here. It's still just times 2 to get this arc is 130 degrees. And totally logical sense here, the other half, let's do it in a different color, the other part of this angle, I shouldn't say the other half, but its supplement is 180 minus 65, which is 115 degrees. And if we multiply that by 2, because this is the inscribed angle of this arc, multiplying that by 2, we get 230 degrees. And no surprise, 230 added to 130 makes a full circle of 360 degrees. Perfect, okay? So it was asking for the measure of AB, so it's that pink 130. Right, down here is a pretty direct application of an angle that is inside the circle but not at the center of the circle. We get that interior angle is equal to the average of the two intercepted arcs, because you have an x over here, they're vertical angles. So the two x angles are opening up to an 85 degree arc on one side and a 145 degree arc on the other. So we get x is equal to 1/2 of the average of the two, or 1/2 of the two arcs added together, right? So this is 1/2 of 230 degrees, or 115 degrees. Okay. Well, we could do that exact same thing with variables in there, right? That same relationship holds true. So this interior angle right here is equal to the average of this arc and this arc. Now we don't have two numbers and we're trying to find the other. Instead we've got, well, it tells us that this angle is x. So the interior angle we're talking about is actually its supplement 180 minus x. So we get that interior angle, 180 minus x, is equal to the average of the two arcs. So the two arcs are the 30 degree arc plus the 2x minus 30 degree arc. Now I don't need parentheses here because it's addition. If it was subtraction, I would need parentheses. All right, so we get that this is 180 minus x equals 1/2 of 2x, right? Because the 30 and the minus 30 cancel out. So 180 minus x equals x, because 1/2 times 2 is 1. And then adding x, we get 180 equals 2x. And so actually in this case it worked out to be that x was 90 degrees. Perfect. I'm going to switch to blue just so we're not so crazy bright here on these problems. Let's do a couple more. So go down here, number 11 is our third relationship that we talked about, right? This is that idea of an angle that is outside a circle. And so we get that angle is equal to 1/2 the big arc minus the small arc. Right? So in this case, it doesn't happen that our exterior angle is the thing we're looking for. In this case, we're looking for one of the others, one of the arcs, but it doesn't matter. The relationship between this angle, the small arc, and the big arc still holds true. We get that the angle x, the angle was x here. The angle, in this case 29 degrees, is equal to 1/2, and I'm going to write the big arc minus the small arc. So the big arc here is 114 degrees minus the small arc here, which is x. Right? So it's the same relationship between the same three things, the exterior angle, the big arc, and the small arc. The only difference is the labeling of which is a number, which is a variable. That doesn't change the relationship. We still plug it in and use the same formula. Now we just have to solve this with algebra. So you could distribute in this 1/2, but instead let's just get rid of all the fractions here by multiplying both sides by 2. So we have 58 degrees equals, these cancel, and now 1 times parentheses, we don't need the parentheses anymore. It's 114 minus x. Adding x to both sides and subtracting 58 from both sides, we get that x equals, that's 42 and 56, I believe. Yeah, there we go. X is 56 degrees. Okay. On the next one, again, it's that same relationship, but now they just give us multiple things with x's. We still get that the angle is equal to 1/2 the big arc minus the small arc. So the angle, just to separate these for you, the angle 34 degrees is equal to 1/2 the big arc. And let's actually use rectangular brackets. They have no different meaning than regular parentheses, but it just, for eyesight, makes it easier to separate which is which. So big arc, 3x minus 2, minus the small arc, x plus 6. And notice I'm using parentheses now around that because I'm subtracting, I'm subtracting the whole group. So I need to distribute this negative in. Okay, so this inside the parentheses becomes 3x minus 2 minus x minus 6, or 2x minus 8. Okay, so writing that down here, I've got 34 equals 1/2, switching to round parentheses, 2x minus 8. Okay, now in this case, I'm going to distribute in the 1/2 just to be a little different than the last time, and because both of these numbers are even. So 34 equals half of 2x is 1x. Half of 8 is minus 4. So adding 4 to both sides, I get x is 38 degrees. So again, it was the same relationship. It's that same thing of x equals half the big arc minus the small arc, so half of b minus a. Okay. Here now we're going to kind of combine all the stuff we've been working on. So now we're using all of our theorems. Again, our first two things we want to check are, do I have an inscribed angle, a and 2a? And second thing is, I have my total of 360, and a half of that is 180, right? Those are the two things you want to always check first. And then if we get into another situation, we'll look at it. So first things first, I got an arc of 110 over here. So I know that its inscribed angle in here is 55 degrees. Okay. And now, if I were to pretend this exterior thing wasn't here, so let's go ahead and erase it. If this was not here, look at what I have, right? Let's just pretend. We already used that 110. Look at what I have. I have an exterior angle here. So I know that my exterior angle, 55, is equal to 1/2 my big arc, x, minus my small arc, 40, and then it just becomes some algebra, right? So again, I just thought about that exterior circle not being there, and visually, yeah, adding that information kind of, confuddles us and makes this, it just kind of makes it more difficult to see and separate visually. But this is what's going on after we found this angle. So 55 equals that. This time, I don't want to distribute it. I don't want to deal with a half of x. So I'm going to multiply both sides by 2. I get 110 equals x minus 40. Adding 40 to both sides, I get that x equals 150. Great. Okay, let's just do a couple more. Now this one comes to a cool idea here. I really like this problem. So this one brings up that separate thing we talked about here, where if you know the exterior angle and you know the total circle adds up to 360, then we could talk about one part being a variable, let's say a, and the other part being the rest of the circle. We're going to use this trick down here. Okay, so here's what we're going to do. I'm going to think about this. I'm going to take a different color here, so we need to be a little brighter. It doesn't matter which one we start with. Let's start with the 40 degree, okay? So I'm going to say that this here is a, and the rest is 360 minus a. So I'm going to say, okay, my exterior angle, 40, is equal to 1/2 my big arc, so that's 360 minus a, minus my small arc, a, right? Just have a 360 minus a being the rest of the circle that is not pink. So now when I take that and I solve for a, I go, okay, well that's this time, oh yeah, let's clean this up inside here. This is 360 minus a, or 360 minus 2a. So I can distribute the 1/2 in nicely. So let's do that. 40 equals, distributing the 1/2, I get half of 360, minus half of 2a is a. So adding the a to both sides, okay, subtracting the 40 from both sides, I get that a equals 140 degrees. Okay, so just erasing this really quick, whoops, I could take this, just erasing this, I get that this is 40 degrees, whoops, 140 degrees, sorry. Okay, so now I'm going to go ahead and erase this 360 minus a, and I'm going to do that same trick to find one of the other two arcs. So over here, let's do it in a different color. Let's do it in green. So let's say the 60 degree exterior angle here is opening to some arc B, right? B being from here to here. And then the rest of the circle we'll just call 360 minus b. That includes the 140 and this unknown portion over here. So again, I'm going to say, okay, that exterior angle, 60 degrees, because essentially this is what I've got here, right? I've got a 60-degree angle opening up to, well, that was a terrible circle, up to B, and the leftover of the circle is 360 minus B. Okay, so 60 equals 1/2 of the big side, so that's 360 minus B, minus the small side, B. Again, that's 360 minus B, that's 360 minus 2B. I'm going to distribute in the 1/2, so I get 60 equals 1/2 of 360, 1/2 of 2B, adding the B, subtracting the 60, I get that B equals 120. So going in here and erasing this and erasing all this, I get that B is 120 degrees, and just through simple subtraction, you could get that this must be 100 degrees, just because the total is 360. We don't have to go through it a third time. But that's a beautiful problem, kind of tying that all together. Okay. Similar, oh, I thought we had one more problem. That's okay. So what I'm going to do now is I'm actually going to do a review sheets in a separate video that just practices a lot of these problems, kind of puts it all together for you. So if you're getting this, awesome, go ahead and do it on your own. If not, join me in the review video of just me working through some review problems.